I've left the other headphones at home, and they actually have better sound than this, but this do. I'm hoping it won't be clicking today. If anybody knows how to get I'm told they're called dead cats that go over the top of this to stop it from. Yeah, I'd love one of those because I've lost it. So I don't know. You've just been immortalised on my YouTube channel, you Lucas. Thanks. Okay, so here's some stuff about cubics. Cubics are beautiful functions that are only a little bit more complex than quadratics. I really want to stress that a lot of the stuff we do at the moment is going to be just a slight extension on quadratics, and we're going to be using very similar stuff. This is typically what a cubic looks like. If you're wondering, it's a bit of a mess, but I wanted to write this so I could then talk about it. If you're wondering which bit is a cubic, that is the black bit there, and I'll just highlight it for you. So this is the cubic function here. This is a pretty standard cubic function, but there are some slight differences that could occur. So a cubic function could start high and finish low. That's one slight difference. Come down here and do that. And the other statement, which is here, is a cubic function might do this kind of wave, turn around, turn back around sort of thing, but it might not. It might just go up and sort of flatten out a bit. It might flatten right out and be flat, but it might just flatten out a little bit and then keep on going. And you'll see some examples of that as well. But here are the facts. A cubic function will have 3 x-intercepts, or it'll have 1 x-intercept. Because it always starts low and finishes high, or starts high and finishes low, it has to pass through the x-intercept, the x-axis once. But it might have 3 if it does that double turn. But it might also do that double turn up here. So it might still have only 1 and still do the double turn. So it could have 1, or it could have 3. Expect to see one or the other. It will have 2 turning points or maybe no turning points. You'll get a pretty good idea of what a no turning point cubic looks like. And they're the ones that can be written in transformational form, like the quadratic transformational form. So we'll see a bit of those. It will have 1 y-intercept, always. It might not be on the diagram you're looking at, but it will exist. There's always, when we put x equals 0 into any cubic, there is a y value that exists for that. But if it's negative a million, then you might be looking at a function that's more over here and it doesn't, you can't see the y-intercept. But it definitely exists. And over here, starts low, then finishes high, or it starts high, then finishes low. They're the features of a cubic that you'll see. And we're going to consider a pretty wide range of these cubics. So I'm going to just, and I know people are copying down, it's on the OneNote. I'm going to talk quickly about solving cubics, which is the focus of today. So here's a cubic. This is actually, I think, example 4, so I'm not going to solve it right now. But you know, last year when you did quadratics and you asked to solve quadratics, and solving means you find the x-intercepts when y equals 0. When you ask to solve a quadratic, you learn how to do it by factorising first, and then you probably learn how to do it by completing the square. And then you got told there's this quadratic formula, and that's the quadratic formula there, and that solves all quadratics. This is actually completing the square on a generalised quadratic and standard form. You get this formula. So then you're like, well, hold on a second, why do they even bother learning how to complete the square and factorise? And that's a good question. This is kind of the why. So in green here I said, is there a cubic formula in purple? And in green, yes, there is a cubic formula. There's lots of different forms. I considered putting it on here, but it's I would have had to zoom in so much that you probably wouldn't have been able to read it from where you're sitting, even here. It's quite a large, substantial formula. There's quite a few different forms, and lots of mathematicians have played with that for many years, but it's never really gotten simple enough to deal with. So we don't really use a cubic formula. Some computing software might, but other than that, we don't use a cubic formula. So we have to learn how to solve in other ways, and the best way really to solve a cubic, and the ones that you'll be doing, is to factorise. Hence why it's so important to learn how to factorise with quadratics, so you can build that skill into your cubics moving forward. So I'm going to talk to you a lot about factorising cubics. There isn't really a completing a square method except for in special cubics that we'll talk about as well. So I've got 4 examples, and then that'll lead you into the first exercise, and you should be able to do it fairly well. So I'm hoping that I don't upset anybody by moving to here. No one's stared me down. So example 1, solve that cubic. Would anybody like to give me some advice on how we might go about solving that cubic, or maybe even give me one of the answers, perhaps, if you'd like to? Alicia? Each bracket equals 0. Do you remember what that theorem's called? That's right. Null factor theorem. Excellent. Thank you, Alicia. And you know what? To be honest, you're not going to be assessed on what that theorem's called. You're going to be assessed on being able to apply the theorem which you've just done. So if three things are multiplied together to give 0, the only way that can be true is if one of them is 0. That's the null factor theorem. So you get three solutions, which we said you can get with a cubic, and those three solutions are x minus 1 equals 0, or x plus 10 equals 0, and that gives us x is equal to 1, or x is equal to 3, or x is equal to negative 10, and you might simplify that by saying x is equal to 1, 3, or negative 10. And they just come straight out of that bracket system there. So you factorise. If you can factorise a cubic, solving it's trivial. The factorising is the hard bit. But you have to remember that null factor theorem and apply it appropriately. And that will actually, the null factor theorem will come up in other areas. When we learn more functions, you'll be dealing with exponential, log functions, periodic functions. You will get situations where your functions are written as a product and equal 0. And if you can apply the null factor theorem, you'll be able to find all of the solutions. And equally, you'll get the same thing when you have your functions written as a quotient, as a fraction. And you'll know that the denominator can't equal 0. So that'll be a hint for you as well about solutions that can't exist. So moving forward, we need to be able to do that. I'm going to leave A on there, but here's example B. Can anybody tell me one solution to example B? X equals negative 7 is the obvious first solution. So we get x plus 7 equals 0, which leads to x equals negative 7. That's the null factor theorem. The other side of the null factor theorem here is that our second option is x squared plus 2x minus 10 equals 0. So we have a linear factor and we have a quadratic factor. If the linear factor equals 0, that's pretty trivial. The quadratic factor equals 0. Now we're back into that quadratics topic and we need to solve a quadratic. Can anybody see a way of factorising x squared plus 2x minus 10? That's the process. I guess can everybody see what that factor pair is? Something plus something equals 2, something times something equals negative 10. Eight times. Oh, 8 times C, but A is 1, so this is the mnemonic version. Yeah. 4 and negative 2 multiply to give negative A. 2.5. They give 2 and 5 give a difference of 3, not 2. Okay, but you see where we're going here? And you see how quickly that happens. So here's my advice for your exam. Unless the exam specifically says, solve this quadratic by factorising, which in year 11 it won't, that only gets done in year 10, then you invest no more than about 30 seconds. Make sure you're good at this process. Make sure you understand numbers well enough to be able to work out, is there anything here? 30 seconds. Invest 30 seconds in seeing if you factorise. If you can't factorise, move on. What are the other two options? Quadratic formula, completing the square. Those two options will both work every single time. But we're going to use the quadratic formula because you can revert to that if you need to. Another thing you could do here is if you're like, I wonder if I can factorise this, I don't know, solve it in your calculator. Use the polynomial solver. Solve it. If you get nice full numbers like integers, then it can be factorised. If you don't get integers, it can't be factorised. Quadratic formula. X is equal to negative b plus or minus the square root b squared minus 4ac over 2a. Is that on the formula sheet? Yeah. No, it's not on the formula sheet, and that wasn't my decision, by the way, so just keep that in mind. QCAA, I'll give you their email if you want. So you need to know that. You need to know that formula there. There's a song. But given I don't like fun, I don't like songs, so you'll have to look that one up yourself. B in this case is 2, A is 1, C is negative 10. We put them in negative 2 plus or minus the square root of negative 2 squared. What did I do that for? That's 2. B is 2. 2 squared minus 4 times 1 times negative 10. 2 times 1. Remember, sometimes you only get one solution to a cubic, not 3. If the discriminant is less than 0, that means there's no solutions to the quadratic. You learned that last year. That means you've only got one solution to the cubic here. But in this case, it is going to be bigger, and we're going to drift into the other working area, but that's all right. Negative 2 plus or minus 2 squared is 4. Negative 4 times 1 times negative 10 is 40. So it's 4 plus 40, so that's 44 over 2. And because we understand surds and we want to use an exact value, we get this. Negative 2 plus or minus 2 root 11. Remember that surd stuff in the end of term 1? 44 divides by 4. It's 4 times 11. The square root of 4 is 2. So the root of 44 is 2 root 11. If you do this in your calculator though somewhat, it'll do that for you. And we're not testing your surge ability here. But the nice thing is here we have a factor of 2. So I've really dragged into the other space. Negative 1 plus or minus the square root of 11 is our solution. Common mistakes. Simplifying this, dealing with multiplying negatives, squaring numbers here. That is probably the most common quadratic formula mistake, getting that right. Make sure you get that right. The second thing here is people would divide 2 by 2 and leave that 2 on there. That doesn't work. So you've got to make sure that you do every term in the numerator is divided by the denominator if you're simplifying. If you can't do that, if you have trouble with that, factorise the numerator. Take 2 out of the common factor and then cancel. Make sure you always factorise, cancel. Factorise first, then cancel. So that's the solution there. In this case, we had a quadratic that was partially factorised. We knew one root, and we knew a quadratic, and then we had to go through, the first one was trivial, and solve the quadratic for the second case. That was example, for some reason I've done example 1, A and B. Now I've got example 2, and then I've got an example 3, but I'll do that later in the lesson. So this is the last one I'm going to do with you now. And I've done this because it looks hard, cubic, not factorised at all, but it's actually more trivial than it might seem. And if you haven't spotted this already, there's a common factor there. So example 2 can be written as x, 3x squared minus 2x plus 17 equals 0. So there was a common factor. And therefore, x equals 0, or, I might move that all back actually, or 3x squared minus 2x plus 17 equals 0. Can somebody watch that clock and tell me when 30 seconds is up? If you're doing your factorising, you look for two numbers that multiply to give 17 times 3, which is 51, and add to give negative 2. Can anybody see two numbers that multiply to give 51 and add to give negative 2? 51's factors are 3 and 17, 1 and 51. Are you able to factorise this? No? Okay, do you see how I'm heading down a dead end now? I'm expecting somebody can tell me 30 seconds. Time's up. Okay, I've taken that time on factorising. In fact, I probably only needed 20 seconds to come to a conclusion then. Now I move on. It's not going to factorise, so I can that idea. X is equal to, and I do the quadratic formula, but you know what? We just did the formula, so why waste time on it now? Because you can all do that. And let's practice doing it in here, shall we? If you can't remember how to solve a polynomial on your graphics calculator, let's try that now. Menu, equation. When you're in equation, you want to select F2 for polynomial. It's a degree 2 polynomial because it's a quadratic. And our coefficients are 3, negative 2, and 17. And then I select F1 for solve. And it says something. No data. Oh, polynomial degree 2. Quadratic degree 2. The highest power is 2. No real roots. That tells you that the discriminant, which is sometimes written as that, is less than 0. There's no real roots. It's less than 0, and that tells you this function has only one solution, and that is x equals 0. And if I sketch this function, and this is just a guess, so it will be permanently on my video, but I'm going to rub it off my OneNote, it might look something like this. Go up, down, and then back up, but only crosses the x-axis at one point. So that's it. And because it crosses the x-axis at 0, I know that's also my y-intercept. So there's some information for you. That's it. Any questions on any of these? Later this lesson, probably at the end of the lesson, I'll do example 3 with you. We'll finish it off. So you've got 20 minutes now to do some of this exercise, and I can't remember what that exercise is.